only, extract the DNA, spin it in this centrifuge tube, and because all the DNA, there's only one heavy version, you get this nice heavy band. The deeper the band, the heavier it is. Make sense? As you spin things down, the heavy things go to the bottom. So there it is. Now, they then transfer the bacteria to a culture media with only nitrogen-14. But the DNA to be replicated before they divide, it has to split apart, and then you add the new nucleotides, which are now made of a lighter nitrogen. You then extract this and spin it, and now notice the DNA. These molecules are a little lighter because they're only half as heavy. You see that? So it's gone up, right? And then you allow them to replicate and extract DNA 30 minutes later. So now, again, these serve as templates. Of course, so you still got some that are kind of this middle weight. We got some lighter ones now. But this one's gone. So now you have, okay, now you got this band is still there because we got these that are kind of image. You got this lighter band now because of these guys. Okay? If this had been the mechanism of replication, you get the heavy band, and it's going to appear all the way through because you got the heavy band all the way. Okay? You get some light ones, you get these two light bands, and once they occur, they're never going to change. If you just fragment the DNA, replicate it, you kind of just get, every generation, this heavy DNA gets diluted out, and it gets lighter and lighter. But they saw this pattern. That confirmed this model of replication. 1955. Now let's get into the mechanism of replication, and it's freaking complicated. Okay, it's not. This is what you teach in Biology 130, the non-science majors, people that are into basket weaving. You know, English lit. Nothing wrong with English lit or basket weaving. I'd rather weave baskets than read English literature. But okay, here's our template strand. Notice the 3' end, we understand that. The 5' end. Here's our template, okay? Bases are added. Now they're added one at a time, but it showed two. It's not my, I don't control this. But again, nucleotides are added according to the base pair rules. And the enzyme that does this, and there's a team of enzymes that replicate DNA, but the enzyme that literally attaches to the template and drives along it, reading the template sequence, that enzyme is called DNA polymerase. This is the enzyme that can read the template sequence and add the appropriate monomer. Now the monomers added, let's identify those. The monomers that are added to form a new chain, they're technically deoxynucleosides triphosphates. They need the 3-phosphates because that's where the energy comes to drive this chemistry. What energetic molecule that's a nucleotide has 3 phosphates? ATP. So in this chemistry, the linkage is formed between each incoming one has 3 phosphates, but 2 are cleaved off, releasing energy to drive this synthetic reaction. Okay, so they power them so that each monomer powers its own linkage. That's called tail end polymerization. It actually allows for editing. It's not perfect. Okay. Here's the next incoming molecule. You see, here's the deoxyribonucleoside triphosphate in case it's got ADNI. So these we abbreviate these, we call them DNTPs. D because it's deoxy, nucleoside triphosphate. They come in 4 versions, of course. When you do this in the test tube, as we'll do in polymerase chain reaction, you have to add a DATP, and a DTTP, and a DCTP, and a DGTP. And here's one right here, the DATP. There's 3 phosphates, okay? And the linkage is between this phosphate of the 5' carbon to the OH of the 3'. There's a linkage right there. And it forms what's called a phosphodiester linkage. You don't have to know that. Do not have to know that. That's for organic chem. Okay? And so the enzyme polymerase will recognize and physically rides the template. It can detect the base from its shape and will allow only the appropriate nucleoside to bind in there, because Only the appropriate one will have the appropriate geometry to hydrogen bond and stabilize the next incoming nucleoside. Okay? And what happens is, again, the linkage between this phosphate and this OH group here, and these two phosphates are released. What's called a pyrophosphate. And some sequencing technologies use that to track this synthesis, but that's for another story. So this enzyme, DNA polymerase, is an interesting enzyme. It's found in all living things. Of course, eukaryotes have a number of versions of it. Prokaryotes only have one version. Okay. This enzyme, let's look at some of its basic characteristics. Help us understand a number of issues here. Okay, there's the pyrophosphate that's released. Okay, to provide the energy, just like the release of a terminal phosphate of ATP to power most of the chemistry of life. Okay, so this hydrolysis of these two phosphates off here releases a package of energy to form that covalent bond. Remember, this is a synthetic reaction. You're reducing chaos, you're reducing entropy, you're going uphill. Those things don't happen spontaneously. You have to have energy to power these synthetic reactions. You don't build order out of chaos for free. Right? This requires energy. The energy is provided by each nucleotide. Think about what that means. It means if the enzyme makes a mistake and adds the wrong base, it can back up and chew off the old base and can bring the next one, and since these incoming monomers always have their own energy, it doesn't matter. I can just pop it right on. Okay? The consequence of that, which I won't go into because it's kind of detailed molecular biology, but maybe some of you will grasp that, I'm sure some of you will, is that during replication that this enzyme drives, the new strand can only grow in one direction, 5' to 3'. This enzyme can stick a new DNTP to 3' end. It cannot attach it to this end. Cannot do it. It can't. It won't. No. You really want to know? Okay, here's why. Because each monomer carries the energy to link itself. Okay? If I try to add one here to this end, there's no 3-phosphate, there's no energy to link to this phosphate, this OH. Can't do it. Does that make sense? Which means the two templates have to be synthesized in the opposite directions, right? One new strand goes this direction, the other one goes in that direction. Whoop. Right? Because of anti-parallel nature. Understand Sie? Here's the enzyme. Its structure has been identified by X-ray crystallography. It does look like a hand with a thumb. If you look at this 3D structure, if you look at the details, of course this is for our textbook, but it looks a lot like that. And it's got a magnesium ion right here in the pocket. It serves as a catalyst. So when we clone DNA in the laboratory, we always make sure we got magnesium in there. Okay. Here's our great template. Okay. Now, there's a lot of other enzymes involved. We're going to start to look at all these. We're going to look at the details of this. We're not just cutting it here. We're going to get into it. This is basic stuff now. Okay. Here's the red is the new growing strand. Notice the new growing strand is growing in the 5' to 3 direction. Here's the incoming nucleoside triphosphate. It's going to be attached to the OH at the 3' end. It's going to attach to that phosphate according to the base pair rules. Okay. Now, other proteins have to unzip the molecule. We'll see there are other proteins involved. Okay. But this is the site here. So this enzyme, again, can only grow the new strand in this one direction. That's one of its characteristics. And actually, that characteristic has been exploited to allow it to clone DNA in the test tube. What's called the polymerase chain reaction. It's formulated in 1981 at Emeryville, California, by the well-known hippie surfer Dr. Kerry Mullis of Berkeley. Former acid head. Admitted acid head. He said it was the best thing he did at Berkeley in his formative years. Not that I'm recommending you drop acid, probably because they had better stuff back then. But pharmaceutical grade, what I heard. he exploited this, in part, this characteristic to develop this, to think of this method on his way to surfing. Actually, he pulled off the side of the road in Mendocino County, took paper out of the glove box, wrote it down, went back, and they did it. Nobel Prize. He gets to surf all the time. All right. The other thing is now. So here's another view of this polymerase. I told you it rides a template because it gets tethered to the template by this clamp. Because otherwise it tends to fall off and stop. You don't want to partly replicate these before cell division. You want a complete copy of your daughter cells. You want to give them a complete inheritance. Okay? And the clamp is attached and removed. There's another protein called a clamp loader that actually will. There's a lot of, even though we're going to get more detail, we're going to leave still a lot out. And when you get to upper division courses, you'll learn more about. But you can see the direction of synthesis is always 5 to 3 prime. And the incoming nucleoside triphosphate is according to base pair rules, always. Although mistakes are made. We'll talk about the repair mechanisms. Okay. Let's talk about some of the other protein components of the replication machinery. So we talk about DNA polymerase as one. We've got another feature here. I'll leave that blank on the board there. Here's some of the other enzymes. It's not exhaustive, not a complete list, but some of the ones at this level. We have DNA polymerase. We also have something called a helicase. So when you see ASE, you know they're talking about an enzyme. This is a protein. This is what unzips the double strand. And it uses ATP energy to do that. Unzip the double helix. Okay? And in the test tube, we can use heat because we're not worried about a cell. And it just kind of ratchets the two apart. Just rides along one, just ratchets it apart. Okay?